Hello everyone, so let's look at writing some balanced reaction equations from equilibrium constant expressions. So it's the other way around than what we've looked at before. So we have a lot of equilibrium constant expressions here, and now we're trying to write the balanced chemical reactions. So in each case I'm going to assume they're in aqueous solution because we're not given whether or not they're Kc or Kp, but we are given that they are concentrations. So I'm assuming they're all in aqueous solution. There's only one little bit of errata that I picked up in the question, so I'll fix it. Maybe I'll fix it in some stage, but this needs to be Cl2 and this needs to be squared. But okay, so let's dive into the question. So for this first for A, if we look at it, if we look at the numerator, we see that it's SO3 squared, and then we have SO2 squared and O2 in the denominator. So that means our reactants are, if we go from just left to right, that means it should be 2 SO2 aqueous plus just 1 mole of oxygen aqueous in equilibrium with 2 mole of SO3, right? Also aqueous. Assuming, it's not Kp. If it was Kp, then these all would have been gases. They can all be gases. They're probably gases. SO2, O2 and SO3 are predominantly gases, but they're given as concentrations, so I write them as aqueous. So, and they're all balanced according to their stoichiometric coefficients. And you can see the powers that they have in the balanced equilibrium constant expression. And if we just quickly scan, then we can see how many sulfurs we need. We see there's 2 sulfurs on the reactant side, there's 2 sulfurs on the product side, and the oxygens we see there's 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 on the product side, right? So everything's balanced, everything's correctly written down, we're good, right? So that's how we write from the equilibrium constant expression, we write down the chemical reaction. Right, so moving on to B, you should notice something interesting or recall something. So in this case, we don't see a numerator and a denominator, we only see one line. And that immediately should imply something to you. That means our denominator is a 1. And you should recall something special about that case. All right, so the only case, or when you see that, K would have been 0 or would have been 1 over something. So if it weren't the products that we were given. So meaning Pb2 plus and Cl minus are the products of this reaction, right? So meaning Pb2 plus, and their concentrations, so that means this is aqueous plus 2Cl minus must also be aqueous, right? They're concentrations, so they must be aqueous. Those are the products, all right? Because otherwise it would have been 1 over or something over them, right? But it's only that. So that is the product that we're given. But what is the reactant? Well, the reactant is 1, right? Because it's product, and the only time when you only see what it is when there is an implicit 1 that is absorbed into the equilibrium constant expression. And the only thing that is usually a 1 is either, well, a liquid or, well, a solid. And the thing that works out here, if you think about it, is lead chloride. Well, lead chloride is a precipitate, so PbCl is a solid that will dissolve into its ions. Precipitate then dissolves back into its ions, and it gets the value of unity then. And if you write this K expression, then you see, oh, yeah, it makes sense. Okay, and everything's balanced. PbCl2, a solid, and it dissolves. All right, it wouldn't make sense to make lead chloride a liquid. Even though that probably would be correct, but I mean it's not a liquid. Lead chloride is a salt, so, and it's hence a solid. So let's look at C. Is there anything that's necessary there? So no. So let's just go from left to right. So we go CO aqueous plus O2 aqueous, and then we get 2CO2 aqueous. Again, these are probably gases, or they are gases. I mean, carbon monoxide, oxygen, and carbon dioxide are all gases. But I mean, for the sake of this question, they're given in concentration form, so I'm going to leave them in aqueous form. And I mean, we can just check that our balancing is correct. So it's 2 carbon, 2 carbon, 4 oxygen, 4 oxygen. So everything seems good to me. So that's straightforward, just like A, we just write it down. Now moving on to D, let's evaluate D. D tells us that we have as products F minus and H3O plus, and as reactants we only have HF. Okay, so let's analyze this a bit. Okay, so HF aqueous, alright, so it's a reactant and it has a concentration, so that's why it's aqueous. And then we have F minus aqueous plus H3O plus aqueous. Alright, so those are the things that we can explicitly see there. What do you notice, right? There's an H and an F on the reactant side, okay, and then on the product side we see an F, and I mean there's at least an H, but there's at least 2 H's and an O missing there. And I mean there's 2 H's and an O, also colloquially known as water, on the left hand side, or meaning the reactant side is missing. And the only time when, I mean, water is missing from an expression, water is a liquid. So this is a case where water has been protonated by an acid and it forms, that's something also we look at when we look at acids and bases, is when the conjugate base forms and water is protonated. So, and you could infer that from the balancing of this equation. And of course the water was left out from the expression because it's a liquid. It also got it also got value of unity. Its concentration doesn't change. It's a very large quantity. This reaction happens in aqueous solution, so hence there's a lot of water available in this reaction, and its concentration is not going to change. It's because of the fugacity aspect that we discussed. So that's how you infer this. You look at it, you write it down, and I could easily infer that water was missing from this expression or this chemical reaction equation. All right. Let's look at E. Okay, again here, starting with the reactants, CCO2 aqueous in equilibrium with 2CO aqueous plus O2 aqueous. We just check everything, 2 carbon, 2 carbon, 4 oxygen, 4 oxygen. Right? So another one is just simply checking whether or not you know how to write from the equilibrium constant going to the equation and checking your balancing. Always good to just check that once again. All right. F. Right, looking at F, we see again, we only see one line, and that implies there must be an implicit 1. So something over 1. Otherwise, it would have been 1 over something. So that means that that again we're given the products of this reaction, and the products of this reaction are two ions once more. Magnesium 2 plus, I almost said manganese, magnesium 2 plus 2OH minus aqueous, because it's squared, OH squared, yes. So what does that form? Well, again, it's like the lead chloride. It must form, it's a salt, a solid. So a solid salt that is, solid salt precipitate that is being slightly dissolved in water to form these two ions. And if we look at the stoichiometry, it says it's MgOH2, so there must be two OHs for every one magnesium ion, because the magnesium is 2 plus, there's two OHs, and that must be a solid because it doesn't appear in the equilibrium constant expression. All right, interesting. Moving on to G, and now you see why I figured out there has to be a balancing issue, or there was an issue with G. If we look what's G's case, so we start with our reactant, so it's CH2Cl2, so carbon has to form 4 bonds, so that means there needs to be at least 2 Cl's. So CH2Cl2, and there's 2 of them in aqueous solution. And that's in equilibrium with CH4, which I'm not quite sure, but how you get into aqueous solution, but that's fine, plus carbon, tetrachloride, also, let's say for now, aqueous solution. These are definitely in their gaseous form, because they're not soluble. So actually for them, let's write them in gas form. We're going to say gas, gas, gas. And now if you check the balancing, you see there's 2 carbon left on the reactant side, 2 carbon on the right hand side, 4 hydrogen, or let's do the chlorines, 4 chlorines left on the reactant side, 4 chlorines on the product side, and then 4 hydrogen, 4 hydrogen, right? So now it's balanced, it's correct, and it makes sense in terms of the K expression. All right, finally we do H. And H, you might also notice again, there's some stuff in the K expression that's not explicitly everywhere. So in H, we see as a reactant, we only have F minus at the moment, aqueous. And our products are HF, aqueous, plus OH minus aqueous. So if we look at the balancing, we see there's an F minus, and there's only an F on the right hand side, on the product side. But there's 2 H's and an O on the right hand side. So that means we need the infamous water on the left hand side. On the reactant side, and water will be in the liquid state, because this happens in aqueous solution. So that means water is present, water is the value of unity in the equilibrium constant expression, and because of the whole fugacity argument, that means it's left, or it's absorbed, its concentration does not change throughout the experiment or throughout the reaction, and hence is why we do not write it in the equilibrium constant expression, but you have to write it in the chemical reaction equation, and hence to balance that. All right, so I hope, let me just get everything in here for if you want to write that down. So you see, it's a bit more difficult when it goes the other way around, because then you have to infer some other things, but it is possible, and I think it's a good exercise because it makes you think a bit more about what's going on, what's going where, and then necessarily writing from the chemical reaction, writing the K expression. So I hope this was an insightful example I'll see you in the next video. Thank you for watching.